Hey, it's Mr. Woodward talking about what you just saw in that last video where I connected a wire to a battery and surrounded it with compasses, and you saw that the compasses moved because the wire produced a magnetic field around it. So in the first case, the compasses pointed in a clockwise direction, which was this one. And then if you were to reverse the direction of the current in the wire by just flipping the battery around, then the compasses would still form a circle, but they would just point in the opposite direction. And so this gives us an indication that surrounding the wire, all the way up and down the wire, there's a circular magnetic field. So if you could visualize that in 3D, it would actually look like this here. So wrapping around this wire in all directions is this circular magnetic field in here. And so physicists got together and they said, hey, wouldn't it be nice if we could come up with some sort of a rule where if we knew the direction that current was going, we would automatically know the direction that the magnetic field was going around the wire. And they came up with this thing called the right-hand rule, which is down here. And the right-hand rule is a just really convenient way of helping you understand the relationship between current and magnetic field. So if you take the fingers of your right hand and you point your thumb in the direction of current, so thumb is in the direction of current, and then you take the other four fingers and wrap them around, the other four fingers will automatically go in the direction of the magnetic field. In other words, they will point in the direction that compasses would point, which is really, really cool. And this works whether you wrap your fingers around so that the fingers go in front of the wire, or if you wrap your fingers around so that your fingers go behind the wire. You still get the same sort of circular pattern. It still would show a circular magnetic field going this way. Now, it gets really tricky to try to draw these things in 3D using these, these looped arrows, because it's sometimes hard to tell if that arrow is sort of going like towards you or away from you. So in addition to coming up with the right-hand rule, physicists also came up with a notation to help you to visualize whether something is looping out of the page and coming at you, or something is looping into the page and going away from you. And so they came up with this, this dot X notation, and I'll show you how it works. So on one side, well, it's helpful to start here. So imagine that you have an arrow, and let me finish erasing this. Imagine that you're doing archery and you have a bow and arrow. And so on this arrow, you have the tail feathers in the back and you have the tip of the arrow in the front. Let me make those tail feathers a little bit more realistic. Okay, tail feathers in the back and the tip of the arrow in the front. So if the arrow was coming right at you, you would see the tip of the arrow first. And the tip of the arrow would just look like a dot if it was coming right at you. However, if the arrow was going away from you, if you were shooting the arrow and the arrow was going away from you towards something else, you would see the back of the arrow. You would see the tail feathers of the arrow. So you would see sort of this X. And so physicists decided that they would use the dot and the X to denote these two things. The dot means that something is coming at you. And in this case, in this orientation, it would be coming out of the page. The X means that something is going away from you, right? The tail feathers of the arrow. And so the X denotes something is going into the page. And so this allows you to visualize in a three-dimensional way, or another way you could think of it is to visualize something perpendicular to the plane of the page, or in this case, the plane of the screen. So in this first in this first drawing, these arrows are coming from these fingers right here. These fingers are wrapping around the imaginary wire, and they're coming at you. And so we would draw this magnetic field with dots to say that, actually, let me show you that those dots would actually line up here at these locations, saying that at each of these locations, the magnetic field is coming out of the page towards you. And then similarly, down here, now on the right side of the arrow, or excuse me, the right side of the wire, now your fingers start to wrap into the page. And so we would draw X's here to say, the magnetic field is going into the page. So between the dots and the X's, you can show something going into and out of the plane of the page. So let's practice that together, because this is pretty tricky and students struggle with this quite often. Let's try this together, if I can just figure out how to make this work. Okay, so here's a picture of that three-dimensional magnetic field surrounding a pencil. The pencil represents a wire with current flowing upwards. You can see that those magnetic field lines would form circles sort of into and out of the page around that pencil. Now, if you replace that with this new notation, now you can see that on the right side, where the arrows go into the page, that's being replaced with X's. On the left side, where the arrows come out of the page, that's being replaced with dots. And then specifically what that means is that on the right side, you've got, let me erase this old stuff. On the right side, the magnetic field is going into the page, so you see those red arrows going into the page. On the left side, the magnetic field is coming out of the page, and so you see those blue arrows coming out of the page. So let's try an example of this now. All right, so here we have a bunch of examples of straight wires going in different directions, carrying current in different directions. And number 4, here's a straight wire carrying current down. And so I've included this picture of my hand holding a vertical wire with current going down. So I've put my thumb in the downward direction, and then my fingers are wrapping around it. So on the left side, my fingers are going into the page. So I would show that with X's. On the right side of the wire, my fingers would then come around back at me out of the page. So I would show dots on this side. And that's exactly how I'll draw it here. On the left side, the magnetic field goes into the page. On the right side, the magnetic field comes back around out of the page. And then connecting those X's and dots is this circular magnetic field. And now let's try number 7. On number 7, you have a straight wire carrying current to the right. So I've got my blue wire here in this photo carrying current to the right with my thumb pointing to the right. And as I wrap my fingers around, my fingers come out of the page on top. So I would draw that with dots up here, and then they wrap into the page on the bottom. So I would show that with X's here, and that's exactly how I'll do it here. Out of the page on top, into the page on the bottom. So that is in general how to draw the circular magnetic field around a wire using dot and X notation.